All right, happy Friday, chemists. Let's get started. A couple of announcements before we jump back into Chapter 19. Chapter 19 is the second law of thermodynamics, entropy and Gibbs free energy. That's where we left off on. I posted midterm 4 practice exams this morning, and I just want to remind you that on Monday we'll have the midterm 4 review session towards the end of lecture, like typical. All of those things are posted, and it's in our common calendar. All right, so do expect that for preparations for our last midterm 4, which in previous years typically is the easiest of all the midterms with these 2 chapters, because we're finally not talking about K that much, big K. Big K is going to come back today, but it's not like the main character of the story. Okay, so yeah, practice midterms for midterm 4. So you have lots to work on this weekend. And just as a reminder, on Wednesday next week we don't have lecture because of Juneteenth. So we only have lecture on Monday and Friday, and then the following week. So we only have 2 weeks left of this semester after today. Yeah. And then there's 2 more lectures that second week, the last week of the semester, and then our final is on Friday. I do anticipate to finish all of the material on that Monday, so hopefully Wednesday will just be a review day. All right, so let's jump back into entropy. There was some confusion about this slide on Wednesday, so I'm going to properly do this slide now. The first part, okay, what is the entropy change of this reaction of the system? Simply, it's just products minus reactants like we've done with Hess's law in previous years. So that part was not, that was the easy part. Taking those table values of the products and subtracting the reactants, making sure to account for stoichiometry. And so what we got was the entropy change for this reaction or for the system was a negative value, and that negative value matches our intuition a bit, in which we see, we start with a bunch of gases, like 1.5 particles of gases, and end up with just 1 liquid particle. So we would, estimate or guess that that this would have a negative entropy because liquids have a lot less entropy present than in a gas sample. So it was the follow-up question. Is this reaction spontaneous at room temperature? So let me do this slide properly. Remember what a spontaneous reaction is. It's one that happens on its own, and it's irreversible. So here's another example of a spontaneous reaction. So don't get confused that I have to light the balloon or I have to light this candle. The idea is once I light this candle, all right, once it's lit, do I have to do anything to keep it going? No, it's going to go on forever on its own until the wax and whatever burns out. So this is an example of a spontaneous reaction, that lighting a candle at room temperature, it happens on its own as long as I light it myself. It'll just keep going until this candle burns out. Or think about it this way. All spontaneous reactions are irreversible. Once I burn this candle down to a nub, is there any way I can get that candle back? No. So it's irreversible, that this is a spontaneous process. This is irreversible. So this is how we answer this second question is this reaction spontaneous at room temperature? It's yes. And then this is when I show the demo. So let's do the demo and check that, is this reaction spontaneous on its own? Yes, I have to, initiate the reaction, but once I do, it just finishes on its own. So let's do that. Let's turn off the lights for once and let's see what it looks like with the lights turned off. Okay, let's turn off the lights. All right. So remember, this is quite a loud reaction, so everyone cover their ears, or you can do the backwards elephant ears, because then you can still hear it, but it's not as loud. All right, ears, everybody. Let's see how it looks in the dark. Okay. So think to yourself, is this a spontaneous reaction once I initiate it? Was that spontaneous? Yes. Was it irreversible? Can I get that balloon back? No, I can't. So this is absolutely a spontaneous reaction. Don't confuse that I had to light it. It's once I lit it, it goes, all right? So, okay, let's put you back on. Okay, moderate projection. Okay. So that is absolutely a spontaneous reaction. It's irreversible. So we can make the conclusion that since this is a spontaneous reaction, then the entropy change of the universe must be what sign? Positive. It must be positive. We just calculated that the entropy change of the reaction of the system is negative. So based upon that, putting it all together, remember, entropy change of the universe is equal to the reaction, so the system, I guess, plus the surroundings. We just deduced, we first calculated that the entropy change of the system is a negative value. We know that this reaction is spontaneous at room temperature, so the universe change must be a positive number. So putting all those things together, we are able to deduce that the entropy change of the surroundings must be a very big, large, positive number, because that's the only way we can get a entropy change of the universe to be positive, to come out to be positive. And so now lastly, we can use the equation here that the entropy change of the surroundings is equal to the negative enthalpy change of the system, so the enthalpy change of this reaction over temperature. So we know that overall the entropy change of the surroundings is positive, so therefore the reaction must have an enthalpy change, like a heat of reaction must be negative. We know this to be an exothermic reaction. Does that match what we just saw? Yes, that the hydrogen balloon reaction is absolutely an exothermic reaction. It's a big fiery fireball. It releases a lot of heat, and so that's consistent with a positive change of the surroundings, that the surroundings increased its entropy much, much larger and was able to compensate the decrease of entropy of the actual reaction that's taking place. All right, so hopefully that clarifies how we were able to come to that conclusion. All right, okay, so let's, that's entropy, so let's talk about Gibbs free energy now. All right, so you know, we were always looking for positive entropy changes of the universe for spontaneous reactions, but now we're going to play around with this new idea, Gibbs free energy, which is just an easier way to think about spontaneity, where everything is in terms of the reaction now. We no longer have to think about the reaction and the surroundings, so the entire universe. That's annoying to do. So let's put everything in terms of the reaction, where Gibbs free energy of a reaction is equal to its enthalpy change, so the heat of that reaction, minus T, the temperature. This value is always in Kelvin. All right, it's always in Kelvin. Kelvin temperatures are always positive numbers because 0 Kelvin is the lowest you can have, and then it always goes up. So you can think of that temperature value will always be a positive number. It'll be either be really small or really large, and that'll be important in a moment. And then finally, multiply that temperature by the entropy change of the reaction. Notice how everything's in terms of the reaction. Very nice. Okay, so. Oh, and then we can do, you know, products minus reactants for any of these things. Do note the units that come out of these. Enthalpy and Gibbs free energy are both in kilojoules, but entropy is in joules per Kelvin. Okay, all right, so this is where we left off, talking about the temperature dependence of Gibbs free energy. Remember, we are looking for now negative Gibbs free energy changes for reactions. That is what predicts a spontaneous reaction. So I have a bunch of different scenarios, and I want us to predict at what temperature range are these reactions spontaneous. So I'm asking you, okay, if temperature is a small number, will delta G be negative? Or if temperature is a big, large number, will delta G be negative? That's what we're looking for now, and you'll see kind of the usefulness of this new Gibbs free energy equation, because everything's in terms of the reaction. So let's look at these two. Let's look at the third and fourth examples first. Let's predict these two reactions. What are the enthalpy changes for these reactions, and what are the entropy changes for these reactions? So this first reaction, what's happening? It looks like solid water to liquid water. On the street, we call that melting ice, right? So think about what kind of energy changes do you need to make that happen? What is the sign of delta H? We're just looking at signs right now. How do you melt ice? You have to heat it. So that means that delta H should be a positive number. right? Now let's look at the entropy changes for this reaction, going from reactants to products. So we're going from a solid to a liquid. So how's entropy changing? It's going up. Yes, because we're going to a liquid phase where there's more, I guess, disorder. There's more free translational motion for those particles rather than in the solid phase. And so then in the fourth reaction, all right, just down, notice how the reaction, this fourth one, is just the reverse. This third one, it's melting of ice, but this, on the street, we call this what? Freezing, yes. So let's get the signs of that out of the way as well. But notice that this is just the reverse of the third reaction. So what you'll see is that the signs change. In order to turn water into ice, you have to remove energy from the system. So we have an enthalpy change of a negative sign. So it seems like, oh, this reaction's exothermic. That actually does happen a bit when you melt ice, or sorry, when you freeze ice. When that phase change happens, that sample's losing energy, and so it gives a puff of heat out into the atmosphere in order for that to happen. So we see that this is, the sample's losing energy, so its enthalpy change is negative, and then the entropy change is also negative. So notice that we reverse the reaction, the signs changed signs. Okay, so how are these signs useful to us? Well, remember, the new equation we're exploring right now is delta G equals delta H minus T delta S. I'm asking, how can we get a negative delta G out? Because that is what will explain to us when this reaction is spontaneous. I already gave you signs of enthalpy and entropy. The only thing we can change now is temperature. So this is how I do it. I just plug in those signs. I think to myself, okay, delta G for this third reaction is a positive delta H value minus temperature, and then entropy is also a positive number, right? The only thing that can change here is temperature. Temperature is either going to be a small negative number, so like a low temperature, it's going to be real cold, or we can have a really high positive temperature, so a large positive number. So in my mind, I literally change the sign of it. When temperature is small, when it's cold. So that. Is delta G positive or negative right now? It's positive because the thing that I'm subtracting it from is a small number. Versus, okay, what if I really exaggerate this? What if we have a really high temperature? Now what is the sign of delta G? It's negative now because the temperature, we're multiplying it by a positive entropy change. We're subtracting a large number. So we can deduce now that delta G will be negative, which is what we're looking for when temperature is high. So when temperature is large, right? Think about what we're saying. What reaction is happening? Would we call that on the street? Melting. We're saying, oh, melting happens when we are at high temperatures. So does that fit like your human existence intuition? Yes, it does. So now let's look at the other reaction, the opposite one. We'll come to the same conclusion where we are asking, when is this reaction, the freezing of water, spontaneous? We are going to do the whole delta G thing again, but we're going to use the signs for this reaction. So enthalpy is a negative value minus temperature times a negative value for entropy. So ask yourself, when does this expression become negative? When temperature is small or when temperature is big? When temperature is small, yeah, so when temperature is really small, we see that it's a negative minus a small negative value, so it stays negative. Versus if we did, a negative value minus a large negative value, this would end up being positive. So the reaction is no longer spontaneous at high temperatures. So what we see is that at low temperatures, the reaction is spontaneous, or you can think, oh yeah, delta G is negative, all right, when temperature is small. What do we call that on the street, the last one? Freezing, okay? So we just proved that delta G is negative for this freezing reaction, turning a liquid to a solid when temperature is really small. So that matches our intuition. We have to cool stuff down to freeze it versus we have to heat stuff up to melt it. All right, so no longer is it just like, oh, we're above or below the freezing point. That's when things are like liquid or solid ice. It actually has to do with the spontaneity of these actual reactions. Okay, so that's the water example. That one's a little bit more intuitive. So let's do these first two and think about this. Okay, so these two reactions are different. This is the generation and decomposition of ozone. All right, the ozone, think the ozone layer in our atmosphere, which does good from protecting our Earth from very energetic cosmic rays from our sun. I gave you the signs of enthalpy here because you don't know them. You couldn't guess what it is. But what you can guess or determine is what is the entropy signs for these different reactions. So this first one, notice how everything's in the gas phase. We're going from 2 particles to 3 particles. So what do you think the entropy change is for that reaction? It is positive, yes, because we're going from 2 to 3. So versus the second reaction, which is really just the opposite of the first one. These two go together. We're going from 3 particles to 2 particles, so entropy change is negative. All right. Okay, so let's do the same exact thing. Ask ourselves, in what temperature scenario does delta G come out to be negative? Because that is what we are looking for. So again, we're doing delta G equals delta H minus T delta S. Place in those signs. So for this first one, we have a negative enthalpy minus temperature, positive entropy, right? So then ask yourself, when is delta G negative? When temperature is really small, is delta G negative? Yes, but what about when temperature is really big? Is it delta G negative? A negative number minus a positive number is always negative. So here we are seeing any temperature, delta G is negative. This reaction is actually spontaneous at all temperatures because delta G is always negative. Notice how we're able to do this is because temperature is in Kelvin and it's always a positive number. So temperature will never change the sign of this delta S term. It only changes the magnitude. Is it big or is it small? And so in both cases, we see that delta G remains negative. So what we can deduce here is delta G is always negative at all temperatures. So this reaction is always spontaneous, always spontaneous at all temperatures, right? It's always negative. All right, so then let's do the next one. I'll do a different color so we can see it. So same exact idea. We are plugging in these numbers. So we have a positive delta H minus temperature and a negative delta S. So what we're doing is taking a positive number and subtracting a negative number. So when temperature is small, delta G is what sign? Positive. Yep, because we're subtracting we're subtracting a negative number. So technically we're adding whatever that number is. Versus when temperature is really big, delta G is also positive. So what can we deduce there? That this reaction is what? Never spontaneous. It is never spontaneous. So in this example, delta G is always positive, regardless of what the temperature is. So what we can take away from this reaction is never spontaneous. It will never happen on its own, spontaneous. All right? So now let's take those answers and actually look at what reactions these are. All right? So the first one is what? We're taking O3. O3 is ozone. So ozone decomposes into just regular oxygen, always, at all temperatures. So we see that the decomposition of ozone is spontaneous, that it'll happen on its own. Once that reaction is initiated, it overcomes its activation energy, it's going to happen on its own. So what we can see here and kind of conclude is that ozone is always decomposing. And what's the sad reality here is look at the second equation. It's what? The generation of ozone. The generation of ozone is never spontaneous, all right? So regardless of, if we just leave a sample of ozone out there or oxygen out there for a long time, it's never going to convert itself to ozone on its own. So that's kind of like a sad reality of, our ozone layer out there. So you might be asking, well, how is ozone made? All right. Even though the second reaction is not spontaneous, it doesn't mean it never happens. You know, you can think energy is like money. Once you have enough of it, you can do whatever you want. And so if you look up how is ozone generated, it is actually generated in lightning strikes, because lightning strikes, tons of energy is present, and it can force this reaction, a non-spontaneous reaction, forward. But the generation of ozone will never just happen on its own. It only happens during like really high energetic events like lightning strikes. So that's why, you know, the depleting of our ozone layer is such a concern. And from a just thermodynamic standpoint, the second law of thermo just tells us that ozone isn't going to generate itself. It's not going to generate itself, but it will decompose on its own. All right, and we're aiding in that by adding other catalysts that push that decomposition reaction faster than what typically happens. All right, so that is how we look at the different scenarios and signs for delta H and delta S, and how we can predict whether a reaction happens or not. So notice that this equation is quite nice to use because everything is in terms of the reaction. Okay, so let's throw back a little bit of the very beginning of the year. So what, like 6 weeks ago, back in chapter 13, when I talked about dissolution processes. Okay, so sometimes when you dissolve a salt, it gets in water, it gets hot. That's an exothermic reaction. Or sometimes you dissolve a salt and it gets cold. It feels cold to you, and it's an endothermic process. So back in chapter 13, you might have remembered me saying that for exothermic dissolution processes, I told you that this was process was driven by enthalpy, all right? And now we know why, okay? When we dissolve a salt in water, that's a spontaneous reaction. So if you think about, okay, spontaneous reactions are when delta G is negative. For an exothermic process, enthalpy is already negative. So it's that negative delta H that is forcing that delta G to be negative as well. So this is why I told you, and I just told you to memorize, that for exothermic dissolution processes, they were driven by enthalpy. And it's, again, because the sign of enthalpy makes delta G negative as well. That is why. So then it was the other scenario for dissolving a salt. Well, what about endothermic dissolution processes? These processes are also spontaneous when you dissolve a salt, but it gets cold. Because if you think about that, if the reaction gets cold for an endothermic dissolution process, doesn't that mean delta H is negative? Or sorry, it means delta H is positive. So it is more difficult to force delta G to be negative. If it's still spontaneous, delta G has to be negative. So what we see for an endothermic process where enthalpy is positive, the only way we can get a negative number come out is if entropy is also positive. The entropy change is positive for that system. And so what we see here is that it's not the sign of enthalpy that is forcing Gibbs free energy to be negative. It's actually the sign of entropy, the positive value. We're subtracting a positive value. So we see that endothermic dissolution processes are driven by entropy because we're subtracting that positive number. So this is finally, I'm explaining you know, that entropy magic wand that I was waving around at the beginning of the year. It actually all has to do with this Gibbs free energy equation and how we can get a negative sign to come out. So let's actually answer these questions. So here's an example, the dissolution of ammonium nitrate. This is what's in cold packs. So when you break open a cold pack, it's just a endothermic dissolution process. That is a process that's driven by entropy, that the entropy change of that reaction is so positive, it forces the reaction to happen, even though you're creating weaker bonds. So here, yeah, in an endothermic process, we see that the mixture actually has weaker bonds than the pure solute and solvent, which is weird. Like, why would we ever want to make something that's weaker? The world is always trying to make the strongest bonds possible, but it's because of the entropy component in Gibbs free energy. Entropy increases so much that it takes over that positive sign of enthalpy, and it still happens on its own. So, that's explaining something that I brought up at the very, very beginning of the year, and it's all about that entropy term. Okay, so let's look at some other ways we can use this equation. Okay, so I mentioned that if you think about the sign of delta G, I said if it's negative, if a reaction has a negative delta G, then that reaction's spontaneous. But if it's positive, it's non-spontaneous. So if we think about what kind of number separates negative numbers and positive numbers? 0. Yes, so something special happens when delta G is 0. The reaction is not, it's basically not spontaneous. It's not spontaneous. Instead, we can say the reaction is at equilibrium, right? So basically you can think, remember what an equilibrium is. It's the forward and the reverse reaction are happening at the same time. So you can think, yeah, this reaction is not quite, it's spontaneous in both the forward direction and the reverse direction. And that is special when delta G is equal to 0. So when we force delta G to be 0 in these calculations, we're saying, oh, this reaction is at equilibrium. And this is useful to us because we can then set this equation. If we set this equation to 0, or we say delta G is equal to 0, if we know the values of enthalpy and the values of entropy, we can solve for the temperature at which delta G is 0. And that is very useful to us because we can determine, oh, at what temperature does this process happen? All right, so what process is this? What do we call this on the street? It is melting, right? A solid water to liquid water, that's melting. So what we can see from thermodynamic information, we can determine at what temperature does this reaction achieve equilibrium. So really what we're calculating is the melting point temperature. So in your head, I hope you know what the melting point temperature of water is. What is it? Or you can think the freezing point as well. It's 0 degrees Celsius, or what in Kelvin? 0 degrees Celsius is what in Kelvin? 273, yes. So that should be our answer. So let's see. So the idea here is I give you delta H, it's right there. I give you delta S, it's right there. And since we know that at the melting point temperature, both water solid and water liquid exist at the same time. So that means we have an equilibrium. So we're going to set delta G equal to 0. And so once we do that, we only have one term left. Okay, what temperature do we need to have to force delta G to be 0? So we just have to be careful with the units here. All right, so we just have one variable to solve for, temperature. And we're going to set all of that equal to 0. Notice that the unit of enthalpy is kilojoule per mole, but entropy is joule mole Kelvin. So we just need to make them match. You can do it any way. You can either change kilojoules to joules, so you can say this is 6010 joule per mole, or you can say that the delta S of fusion is 0.022 kilojoule mole Kelvin. All right. Regardless, you just need to make sure those units match. I'll just put both in kilojoules. So what we get here is delta H minus T delta S, set that equal to 0. So 0 equals 6.01 kilojoule per mole minus temperature, entropy change, which is 0.022 kilojoule mole Kelvin. All right, and so solve for that temperature, and you get that the temperature comes out. So I think here, if you move things around, temperature is equal to, I think, entropy change. Wait, no. Yeah, enthalpy change over entropy change. That's what ends up happening when you set delta G equal to 0. And what you get is the temperature that comes out is 273 Kelvin. So we just kind of proved that the temperature at which solid water and liquid water are at equilibrium, or the melting point temperature of water, is 0 Kelvin, or 0 degrees Celsius, or 273 Kelvin. So thermodynamically matches our observations of what we see in the world. Our observations, we know ice forms or melts at 0 Kelvin, and we prove it with the thermodynamic data as well. All right, so yeah, this idea of setting delta G equal to 0 is like we can find melting point or freezing point temperatures. We can also find boiling point temperatures. Oh, that's the next slide. So actually, before I move on, so we know that this reaction is at equilibrium when the temperature is equal to 273 Kelvin. We know this because delta G is equal to 0 at that temperature. So let's ask ourselves, what do you think the signs of delta G and is this reaction spontaneous at different temperatures? So let's pretend we're above 273 Kelvin. We're above that equilibrium temperature we just calculated. What does our intuition say? If we're above 273 Kelvin, does this reaction happen? If we're above 0 degrees Celsius, solid to liquid, what is that called? Melting. So, does this reaction happen above 0 degrees Celsius? Let's say we're at 300 Kelvin. Let's say we're at, what is that, 27 degrees Celsius. Yes, this reaction should happen. So that means the forward reaction is spontaneous, okay? So doesn't that mean that the sign of delta G must be what if this reaction is spontaneous? It should be negative. You don't have to guess. Just plug in that number and check for yourself, all right? So I already told you delta H and delta S. Just plug in, let's just use an example. Let's say 300 Kelvin. Ask yourself, what is delta G when the temperature is 300 Kelvin? It should be negative in this case. So putting in those numbers, I'll put this in joules. So 6010 joule per mole minus the temperature, so 300 Kelvin, times the entropy change, which is 22 joule Kelvin, right? And so this term, if you calculate that, I think is equal to 6,660. All right, or something like that. So we see, yes, in fact, we get a negative number come out if we plug in a temperature that's above that equilibrium temperature, that this reaction becomes spontaneous. We can just plug in a fake number. Or let's ask ourselves, what if we're below 0 degrees Celsius? Does this reaction happen below 0 degrees Celsius? No. No, this is melting of ice. You're saying, oh, water melts below 0 degrees Celsius? No, that doesn't happen. But think about it the other way. If the forward reaction is not spontaneous below 0 degrees Celsius, what about the reverse reaction? What is the reverse reaction? Liquid to solid. That's freezing. So it seems like below the freezing point temperature, 200 Kelvin, we see that the reverse reaction is actually spontaneous. Right? But if we, take this reaction as is, we see that the delta G ends up being a positive number, all right? That means that the forward direction is not spontaneous, but that means the reverse direction is spontaneous at this temperature. We can check it for ourselves. Let's just, place that number, so the same exact idea here, we're gonna place that number inside of our delta G equation, equals 6,010 joules minus 200 Kelvin times that entropy change. And so if you calculate this T delta S term, I think it's something like 4,000 joules. And so what you see is a 6,000 number minus a 4,000 number, a positive number comes out. So at temperatures below the freezing point temperature, the forward direction is not spontaneous, but that means the reverse reaction is spontaneous. And I hope you can relate that to what you understand of how we make ice. Ice melts above 0 degrees Celsius, but it freezes the reverse direction below that temperature. And so again, relating, our observations of real life, but relating it to the second law of thermodynamics and the sign of delta G. All right. Okay, so that's plugging in fake numbers to estimate those ranges, all right, of when processes happen. Okay, so let's do one more. Okay, same idea. Reactions at equilibrium when delta G is 0. So let's determine what temperature is this reaction at equilibrium. So turning liquid water into gaseous water. So what property are we calculating? The temperature to do what? Boil water. Yeah, because we're taking a liquid to a gas. Yeah, so we're going to calculate the boiling point temperature of water instead. So that means I need to set this equation equal to 0, right? And we need to figure out what is delta H, what is delta S, and then we can figure out what that temperature is. But notice here, did I give you the enthalpy change for this reaction? Did I give you the entropy change for this reaction? In the previous question, I did, right? I just gave you them. I gave you the enthalpy and entropy change for the reaction, just straight up. But in this question, I didn't. But what did I give you? I gave you formation values instead. I gave you table values, all right? So this question is made a little bit harder because I didn't give you the enthalpy and entropy changes for the reaction. You have to figure it out for yourself. How do you do that? If I give you these table values, products minus reactants. So I have to do products minus reactants for delta H and delta S first, and then plug it into that delta G equation. So let's just do that. Delta H for this reaction. So here, the gas is our product. The liquid is our reactant. So I'm going to take the first line and subtract the second line. So we see delta H of this reaction is negative 241.82 minus negative 285.83. And that equals something. Delta S for this reaction, again, products minus reactants. So the gas minus the liquid. We are not going to use this column. We actually just need to use delta H and delta S, or sorry, the absolute entropies here. So first line is 188.83 minus 69.91. And so we get that the enthalpy change for this reaction is 44 kilojoules per mole. Or I'm just going to actually just put kilojoules. And then the entropy change for this reaction is 118.92 joule Kelvin. All right, and so those are the two values that are going to go into my delta G equation. So the previous question I made it a lot easier because I gave these to you straight up. But in this one, you can products minus reactants first to get them yourself. And calculate the temperature needed to achieve a delta G of 0. So doing that, we're going to do 0 equals delta H, but do make sure that the units match. All right, so right now, delta H is in kilojoules, entropy's in joule Kelvin. So I'm going to convert the entropy one to kilojoules. So this is 0.11892 kilojoule Kelvin. So do make sure that they match. So 0 delta H minus T delta S. You can rearrange this and just get temperature equals delta H over delta S. So enthalpy, so enthalpy is 44.01 kilojoules. Entropy is 0.11892 kilojoule Kelvin. So notice that the kilojoule units cancel. And then we have a Kelvin, a 1 over Kelvin in the denominator, so a Kelvin temperature comes out. So what we get here is that the temperature needed to do this, oh, where's my calculator? What we see, oh no, did I not bring it? Dang it. We get a temperature, so it's not quite 373. I think we get a number like 370 Kelvin. And so if you calculate the Celsius temperature, you actually get a temperature of 97 degrees Celsius. So you might be thinking, oh, but I know that the boiling point water on Earth is 100 degrees Celsius. So why did we calculate 97? Well, because we used formation values. Remember when we used these table values? These table values are measured at standard conditions. Standard conditions. That means that the temperature is 278. So what we see here is that these table values weren't measured at 100 degrees Celsius. So what we see is that these values actually do change a little bit with temperature, but we're making an assumption here that enthalpy and entropy changes do not change that much with temperature. So that's why our answer is not exactly 100 degrees Celsius, but it's fairly close. So we're going to make this approximation a lot. We're often going to approximate that the entropy and enthalpy changes for a reaction do not change, but what we'll see here is that delta G does change with temperature. All right, does change with temperature. So that's very, very important. All right, we're going to make the assumption enthalpy and entropy don't change with temperature, but delta G does. And that's going to come up in a little bit. All right, so let's keep going. All right, so just kind of summarizing, you know, all the equation we've used so far. Do memorize products minus reactants. I'm not going to give you that equation. Know that if I give you those table values, formation values, you can figure out the enthalpy change or entropy change for a reaction simply doing products minus reactants. We looked at how we relate Gibbs free energy to enthalpy and entropy changes and temperature. And then coming up, we're now going to talk about how Gibbs free energy relates to K, big K. So big K is coming back, all right? And then finally, you know, we talked a lot about standard conditions, 1 molarity, 1 atmosphere of everything. So we'll do some calculations where we're not quite at standard conditions, but we can still use these equations to help us predict what's happening, all right? So yeah, big K is back. So let's talk about big K. All right, so, you know, I said if delta G is negative, we know that the forward reaction is spontaneous. We've kind of used that language before, like when I've said that, oh, if K is a really big number, big K, if big K is a large number, that means there has to be a lot of what at equilibrium? Products. There has to be a lot of products if K is really big. So how do we achieve that? Well, if the forward reaction is very spontaneous, that's how we get a very large value of K. So what we'll see here is that delta G of the reaction, when we use table values, is actually related to the magnitude of K. So remember when we talk about standard conditions, 1 molarity of everything, all right? So if we think about this chemical reaction, all right, this is an equilibrium. So we have nitrogen reacting with hydrogen to give us ammonia. And if, if this was chapter 15 or 16, I would say like, okay, K equals 9, all right? But if we are at standard conditions, think about what are the concentrations of everything at standard conditions. At standard conditions, we have 1 molarity of everything. 1 molarity of nitrogen, 1 molarity of hydrogen, 1 molarity of ammonia. So at standard conditions, we are actually not at equilibrium. At standard conditions, if we do products over reactants, we can simply do, okay, the concentration of ammonia squared over nitrogen over hydrogen. We just said at standard conditions, everything is 1 molarity. So Q at standard conditions is actually 1, right? So is this reaction, our synthesis of ammonia, at equilibrium at standard conditions? It's not, no, because we have 1 molarity of everything. In which way? Just predict, okay? If Q is 1, but the reaction wants a K of 9, which way does the reaction have to go to achieve that? If we start at standard conditions and move towards equilibrium, which way does the reaction have to go? Forward. Because if Q is less than K, you need to make more products. So the forward reaction has to occur. So now relate this to delta G. Okay, if Q is 1, but we want to be a K of 9, the forward reaction has to occur. So what should the sign of delta G be? Negative, and it is. And that's what our table values tell us, that for this reaction, we will see, oh, delta G for this reaction is a negative, some type of negative number. And the reason it's negative is because if we start at a Q of 1, if we start at standard conditions, the reaction must move in the forward direction to achieve chemical equilibrium. And that is what the table values mean, all right? And so the equation we use to relate the Gibbs free energy for a reaction to K is this new equation. Delta G equals negative RT ln K. This R is the energy term, R 8.314 joule mole Kelvin, because Gibbs free energy is an energy term, right? And temperature is always in Kelvin. And so what the trend is here, if you ever use table values and are given, if you're given values for delta G of a reaction, if delta G is a negative number, what we'll see is that K is really large. That kind of makes sense, right? Because a large K means what is mostly present at equilibrium? Products, so you have to go in the forward direction. Versus if you have a really small K, is the forward reaction very spontaneous? No. So that means the reverse reaction is actually more spontaneous, so you'll see a positive value of K, right? So, but all of that trend also comes from this equation itself, all right? So yeah, the signs of K basically tell us if we start at standard conditions, so Q of 1, which way does the reaction have to go to achieve equilibrium? If K is really big, like a big positive number, has to go forward. Delta G is negative. But if K is a really small number, the reaction has to go in reverse and make more reactants. All right, so this is, we'll see is that delta G, this table value is related to K. But the idea here is we don't have to start at standard conditions. We can also start at any conditions. And so what we get is a new equation where we can calculate delta G at any conditions. So notice how this delta G has a knot on it. That knot means table values. It means start at standard conditions. But this delta G means at non-standard conditions. So you can start at any conditions and use this second equation. The second equation helps us predict how does a reaction have to proceed at any given condition, not necessarily standard conditions. But notice how this delta G equation without the knot still has delta G with the knot in it. And this will be an idea that we'll do again in chapter 20, electrochemistry. We see an equation very, very similar to this one, where we can calculate the free energy change of any given condition, even if they're not at standard conditions. And what we'll see here is how a reaction has to proceed to achieve equilibrium matches exactly what Le Chatelier's principle predicted all of this time, right? If I add reactant, the reaction shifts forward, right? We did that in chapter 15. So now just kind of expand on that a little bit. If I add reactant and the reaction shifts forward, what must the sign of delta G be at that moment if the reaction goes forward? Negative. Yep, yeah. And so we'll prove that mathematically now. Okay, so let's do an example. All right. So I give you the KSP for calcium hydroxide. So remember, this KSP represents a chemical equilibrium. Calcium hydroxide solid gives you calcium 2+ and 2 hydroxides. We know that KSP for this reaction equals the calcium 2+ concentration times the hydroxide concentration, but it's squared. Right? So let's calculate the delta G for delta G naught. Notice how I have naught in there. That's very important. For this reaction, this saturated solution at 298 Kelvin. So since I'm asking you what is the free energy change at standard conditions, that naught means, you know, table values. It means standard conditions. We can just go ahead and use this first equation because that delta G has that naught present. And so what we see here is that delta G naught is related to the natural log of K for the reaction. I gave you K of this reaction. And so since all of this is happening at 298 Kelvin, I can just go ahead and use the equation delta G naught equals negative RT ln, specifically KSP. We know KSP, we were given it. R is a constant, we know temperature. So simply we just plug in those numbers. R is 8.314 joule mole Kelvin. Temperature is 298 Kelvin, because I told you that. and then natural log of KSP. So this is 4.8 times 10 to the negative 6, right? Before we even calculate this, K is a really small number. So what do you think the sign of delta G is going to come out to be? If it's really small, is the forward reaction very spontaneous? Nope. So is delta G going to be negative? Nope. It's probably going to be positive, meaning that the reverse reaction is more spontaneous. And that's exactly what we get. We get 30.4 times 10 to the 3 joule per mole. But, you know, that's a fairly large number. Typically, we like to put these numbers in kilojoules. So this ends up being 30.4 kilojoules per mole. And this is a positive number, and that reflects the small, this very small value of KSP. Right? So since this reaction is at equilibrium, what that means is that Q equals KSP in this saturated solution. It means that the concentrations of calcium 2+ and hydroxide are such that when you multiply them together, you get the same value of KSP out. That is what a saturated solution is. We're at equilibrium already, that we've achieved those KSP conditions, right? If we're at equilibrium, Q is equal to KSP. But let's think about like Le Chatelier's principle and the point of Le Chatelier. Le Chatelier's principle said, oh, well, what if we disrupt an equilibrium? When we disrupt it, are we at equilibrium anymore? No. And what Le Chatelier's principle predicts is how does the reaction have to adjust itself to get back to equilibrium? So the idea here is like, let's say we added calcium 2+ to this reaction, or to the saturated solution. We know that adding calcium 2+ pushes the reaction backwards because of Le Chatelier's principle. And the reason is because Q changes the moment we add calcium 2+. Q changes the moment we disrupt this equilibrium with concentration change. But what we say here is the moment we add calcium 2+, only delta G changes, not delta G naught. This delta G naught is a table value that comes from, you know, standard conditions. Standard conditions. It's a table value. That number never changes. It's like saying K. The value of K never changes as long as we stay at the same temperature. But what we can do is change the concentration such that we're not at equilibrium anymore. And oftentimes we'll want to predict which way does a reaction go. So what we see is that the moment we disrupt an equilibrium, only delta G changes. And then that's when we want to use now this second equation when we're not at equilibrium anymore. We're actually at Q conditions. This is where the second equation comes into play, all right? And that's what's coming up on the next slide. When do we use this second delta G equation? Notice how this one does not have the naught on it, and that's deliberate. So on an exam, or like a question, you see delta G without the naught, it means you're at non-equilibrium conditions, and that's deliberate. Okay, so let's do the next one. Okay, so let's try this. So it's the same reaction. Here's KSP again, and here's delta G naught. Notice that these two values, they are related to one another by this first equation. They're related by delta G naught equals negative RT ln K, right? Those two properties are related to one another. So in these situations, we're making solutions that may or may not necessarily be at equilibrium conditions. So we're going to use these concentrations and use kind of our intuition to predict what should we observe. So in this first one, we make a solution that's made to be, okay, 0.005 molarity calcium. Okay, that should be a 2+, and hydroxide 0.05 molarity. So I'm not quite sure if this is at equilibrium or not. So what we're going to do is actually calculate Q given these concentrations. So calculate Q and compare it to K, just like we did in chapter like 15 or 16 or whatever. So go ahead and place those concentrations in 0.005 times hydroxide 0.05, but that is squared, remember that? Right, so that number is squared. And so I get a Q of 1.25 times 10 to the negative 5. all right? That is my Q. Compare that to K. KSP for this reaction is 4.8 times 10 to the negative 6. So right now, I have made a solution where Q is larger than K. Do you agree that Q is larger than K right now? Like what I've produced, Q is larger than K. So go back to chapter 15. And I ask you, if Q is larger than K, you have too much what right now? Products. If Q, like what I have right now, is a bigger number than K, I have too much products. So if this is my reaction and I have too much products, which way does the reaction have to shift? Backwards. Yes, if it goes backwards, what should our eyeballs see if the reaction shifts backwards? A solid is produced. Yeah, that's what we're going to see. So here, Q is larger than K, too much product. So what we see is that the reaction shifts backwards. And we should see a product form, all right? And we should see solid form. So now relate it to thermodynamics now. If the reaction shifts backwards, what must the sign of delta G be at these conditions if it goes backwards? Positive, yeah, because if the reaction went forward, delta G would be negative. But because this reaction went backwards, delta G is actually positive at this moment at these Q conditions. So let's prove it, all right? We're going to prove it using this second equation and calculate what's delta G at these conditions. So notice all the values we need. We need delta G naught, which I already gave you. We calculated that on the previous slide. It's right there. So it's that 30 number. And we're going to add a factor of RT ln Q. Q is the concentrations that were given here. So we have all of those terms. So notice we are calculating delta G without the naught. So because we're at non-equilibrium conditions. And this is equal to delta G naught plus RT ln Q. So all of this together. And notice, so be careful here because R is in the unit of joule mole Kelvin. So delta G naught needs to be in the unit of joule per mole. But notice right here it's in kilojoules per mole. So do make sure that everything is in joules. So this is 30.4 times 10 to the 3 joule per mole. So do make sure all of that works out. So delta G without the naught is 30.4 times 10 to the 3 joule per mole plus a factor of R, so 8.314 joule mole Kelvin. Temperature, this is 298 still Kelvin, and then we're going to plug in that ln of Q, the Q that we just calculate. So natural log of 1.25 times 10 to the negative 5. And so what we see here is that when you calculate this, you get it right there. So when you add this number, this factor of RT ln Q, you do in fact get a positive value of Q come out, right? And so that is consistent with the reaction moving backwards. You have too much product. When Q is larger than K, the reaction goes in reverse. So delta G without the naught is a positive number. So let's do the opposite direction now. Let's say we make up a solution of calcium and hydroxide again. So this is 2+. Wonder how long that mistake has been there. So same idea, but we're going to see the other scenario. In this case, we are using the concentrations given. So technically, we are solving for QSP because we're not necessarily at equilibrium conditions. So this is 0.001 times 0.01 squared. So I think Q is equal to 1 times 10 to the negative 7. So compare this to K. K is 4.8 times 10 to the negative 6. So Q is actually smaller than K. So what does that mean about this reaction? If Q, right now, you have a set of concentration ratio where Q is smaller than K, you have too much what? Reactants. You can say you have too much reactants, or you can think I don't have enough products. Right? I don't have enough products because Q is a smaller number than K. So that means that which reaction is spontaneous? The forward reaction is spontaneous. I'll think not enough product is present. All right, so the reaction shifts forward. So what should we predict the sign of delta G be at this moment? If the forward reaction is spontaneous, it is going to be negative. And of course, now if you plug in those same numbers again, you will get that delta G is negative. So we're going to use the exact same equation now, but all we're going to do is just change the value of Q at these conditions. So notice that it's the same exact thing. So delta G equals delta G naught, so the table value. So 30.4 times 10 to the 3, again, joules, plus a factor of R, 8.314, temperature, 298. And the only thing that changes here is we're doing ln of this new Q, 1 times 10 to the negative 7. And what we get is a negative number comes out, right? This will always happen. Delta G, without the naught, will always be negative when Q is less than K. That's just a mathematical fact based upon the equation that we use. Versus if Q is greater than K, like in our first example, if Q is greater than K, delta G without the naught is always going to be a positive number, all right? So basically, mathematically, we are proving why Le Chatelier's principle works, and we're expanding on that. You know, it's not just, oh, you add product, the reaction goes in reverse. It's actually, oh, you add product, Q is now larger than K, delta G is a positive number at that moment. So we're expanding on it in terms of the second law of thermodynamics. And we can use it, this equation, to explain any phenomena where we are comparing Q conditions to K conditions. Okay, so let's put that all together and ask ourselves, does delta G increase, decrease with these given scenarios when we add hydrogen to these reactions? I want you to think about this in terms of Le Chatelier's principle, because the signs of delta G will match what Le Chatelier's principle says. Notice that I'm asking about how does delta G change. So this means non-equilibrium conditions. I'm not asking you about delta G naught. I'm not asking you about that, because that number just has to do with how big K is. Here, this equation, the second one, talks about non-equilibrium conditions. So Le Chatelier's principle, Q conditions. So let's look at this first reaction, and what we're doing, how we're disrupting this reaction is adding hydrogen gas. So here we're adding hydrogen. So go back to a simpler time, chapter 15, and ask yourself, you add hydrogen, which is a reactant. Which way does the reaction go? Forward. Right? So based upon that, what must the sign of delta G be at that moment? Has to be negative. Yeah, so delta G must be negative the moment we add hydrogen. Okay? And so also think about it this way, all right? Hydrogen's a product, or sorry, no, a reactant. So when you calculate Q, so think about K. K is products over reactants. If you're adding a reactant, that means the denominator is becoming a bigger number. So that means Q is becoming a smaller number. So the moment you add hydrogen, we see that Q becomes less than K. The moment we add hydrogen, because we're making a number on the denominator bigger, right? Because, yeah, Q is simply just products over reactants, all right? So in this example, what we're seeing is, okay, Q is less than K, so delta G is negative. When Q is less than K, I don't have enough products, so the reaction must move forward. So delta G is negative, where the forward reaction is spontaneous. So we see here, delta G naught never changes. Never changes. Everything I'm talking about right now is just delta G. Delta G naught never changes because it's just based upon K. K never changes. That value, that's just like the value you're trying to achieve, but how we use Q. Think about how we use Q is like analogous to how we use delta G without the naught. Delta G naught is related to non-standard conditions, non-equilibrium conditions, so that's when we input Q values. But because delta G naught is just related to K, that's just a standard value that's always used at 298 Kelvin. Okay, so let's do another example here. Again, we're going to add hydrogen, but this time hydrogen's a product. So adding a product to this chemical equilibrium should push the reaction in reverse. So in order to be consistent with the second law of thermodynamics, what must the sign of delta G be at that moment? Positive, yes, if it goes in reverse. Also think about this in terms of Q and K, all right? That the moment you add hydrogen, hydrogen's a product. In the K expression, products go on the top. So we're adding hydrogen, we're increasing the concentration of products, so Q actually becomes larger than K since we're adding more products. So in this moment, Q is actually greater than K. So that is why we see delta G is a positive number. If Q is greater than K, I have too much products, so the reaction must go in reverse, right? So that's putting it all together, and this is just kind of like the mathematical concept behind using delta G equals delta G naught plus RT ln K. That's just how that works, right? Because delta G naught is related to K. Plus RT ln Q. Okay, let's write this out correctly. Delta G equals delta G naught plus RT ln Q, where delta G naught is equal to negative RT ln K. And so this is where the idea of, oh, if Q is greater than K, mathematically, delta G must be positive. So what we're doing is just comparing what are the magnitudes of K and Q, and that's how we get those different signs of delta G come out, but it all matches Le Chatelier's principle as well. All right, so, okay, let's put it all together. A little bit more math. So that one was more conceptual. Let's just do the math ones. Okay, let's use the provided information and calculate the equilibrium pressure of CO2 of this reaction at equilibrium at 225 degrees Celsius or 298 Kelvin, all right? So 298 Kelvin, this is at our standard temperature. Wouldn't you agree? Standard conditions is includes 298 Kelvin. So that means if we're at a standard temperature, we can go ahead and just use the standard values that are given in the textbook. We can go ahead and use those thermodynamic values because those are measured at standard conditions. So I know there's a lot going on here, so let's take a look at this. So specifically, I'm asking the equilibrium pressure of CO2. Let's look at this reaction. Let's calculate what is the K of this reaction, specifically the Kp of this reaction. All right, products over reactants. Look at our products. Look at our reactants. The K for this reaction only includes CO2 gas, right? Everything else is a solid. So what we see here is that the equilibrium constant for this reaction is equal to the pressure of CO2 that we need, right? So it seems like, oh, I can figure out the equilibrium pressure of CO2 if I just figure out what is K. So if you look at all of our equations that we can use, this is the first equation, that's what we're going to use, because the K in this delta G naught expression gives us our equilibrium pressure that we need. So we're going to use that first one. We can also use this first one because notice this is delta G naught. That naught means standard conditions. We are at standard temperature, so we can go ahead and use it. But we have a problem. Did I give you delta G of this reaction? No, I did not. So what we're going to do is simply do products minus reactants. So here are my two products. Here's my one reactant. I'm just going to go ahead and do products minus reactants to get delta G of this reaction. And I can do that because we're at standard temperature. So because remember this table is at standard temperature, standard conditions. So delta G of this reaction is equal to the two yellow things minus the pink thing. So negative 187.9 plus negative 394.4 minus negative 625.5, all right? So we can go ahead and use the table value. Delta G, oh sorry, this should be a naught. For this reaction is positive 43.2 kilojoules per mole. Or we can say this is 43.2 times 10 to the 3 joules per mole. This is important because we're not done yet. This is delta G of the reaction, but I'm actually asking you what is K of this reaction, what is the equilibrium pressure. So the last step here is, okay, let's take this value and plug it into delta G equals negative RT ln K, where we are going to solve for K in this case. So delta G equals 43.2 times 10 to the 3 joule per mole minus or equals negative 8.314. T is 298 because we're at standard conditions, ln K. So we are solving for K. If you move some things around, I think you get that K is equal to, ln K is equal to negative 17.4. If you move those values around, to undo the natural log, you e both sides, and so e to the negative 17.4 gives you this very, very tiny number. That when you isolate K, you get that K is equal to, 3 times 10 to the negative 8, so a very, very small number. And that makes sense that this reaction has a very positive value of delta G. The forward reaction is not spontaneous, so you shouldn't make that much CO2. All right, at equilibrium, right? And so what we see here is when we solve for K, that is equal to the equilibrium pressure of CO2 because that's the only thing inside that equilibrium constant. All right, so that is using delta G naught. Remember, this is at standard conditions, so 298 Kelvin is standard conditions. We can relate that table value to the K, the equilibrium constant for that reaction. So let's do it a little bit differently here, all right? So this is actually the exact same question. I'm asking you, what is the equilibrium pressure of CO2 for this reaction? But notice I gave you different information. In the previous question, I gave you the information right here. I gave you delta G values. Notice here, delta G formation values. But in this question, I'm asking the same exact question. But did I give you delta G values? I didn't. I gave you delta H and absolute entropies, right? So that's an issue. Because recognize that in order to answer this question, I need to figure out what is that delta G naught, okay? You can figure out delta G naught doing products minus reactants. If I give it to you, those delta G values. But in this case, I give you enthalpy and entropy values instead. So we're actually going to use this third equation here. All right, don't discount that Gibbs free energy is also related to enthalpy and entropy change for the reaction. So we're going to answer the exact same question. It's just going to be made a little bit more difficult because instead of calculating delta G outright, we're going to calculate delta H and delta S and then figure out what delta G is and then figure out what K for this reaction is. So notice we are going to do products minus reactants again, but this time for delta H and delta S of the reaction. Then we're going to use this first equation. We're going to use this equation to figure out, okay, what is delta G, and then we'll plug in that delta G into that first equation there. That's what we'll do second to calculate what is K. So in this case, we're kind of really using all of the skills we've learned thus far, that delta G is related to enthalpy and entropy changes as well. Okay, so let's do this. So delta H of this reaction is products minus reactants. So I'll just highlight these. There's my one reactant. There are my two products. So I'm going to do the two pink ones minus the yellow one. So delta H of the reaction is negative 217.3 minus 393.5 minus 699.1, and that equals something. Delta S of the reaction, products minus reactants, 68.7 plus 213.6 minus 131. Yeah, that's it. And so what you get is that the enthalpy change for this reaction is 88 kilojoules per mole, and then delta S is 151.3 joule mole Kelvin. So this is delta H, that is delta S. These two values I can use to calculate what is delta G of my reaction, right? Where we're going to use this first equation. Now I know delta H, now I know delta S. What is temperature? Well, we are at standard temperature, standard conditions here, so we're at 25 degrees Celsius. We are at 298. So I know what temperature is as well. It's 298. So I'm going to use these two values and calculate what is delta G at these conditions. Do make sure that these units match. I'm going to convert delta H to joules. So this is 88.3 times 10 to the 3. So delta G for this reaction, so delta H minus T delta S, is equal to 88.3 times 10 to the 3 joule per mole minus 298 Kelvin times 151.3 joule mole Kelvin. That's entropy. And so what we get is a very familiar number. It is 43.2 times 10 to the 3 joule per mole. That is what you calculate. Look back on the previous slide. We just went a long roundabout way to get the exact same number, all right? That delta G for this reaction is 43 kilojoules. Look back at this question. If you just started with those delta G of formation values, you would also get 43 kilojoules. I just gave you a more roundabout way to do it, but I want you to recognize that those enthalpy and entropy values also give you your delta G values given different temperatures. In this case, we're at standard conditions, so we get the same exact number. Though this isn't our answer, we have to do one last step and do delta G equals negative RT ln K. But solve for K and you get the exact same answer as we did before. We just use delta H and delta S to do it for us. All right, so let's do one last example of using all three of these terms and answer kind of the very last entropy magic wand that I waved around. We saw back in chapter 13 that most solids become more soluble at higher temperatures. So if we related that to K, we would say, oh, at higher temperatures, K becomes larger. Okay, you dissolve more stuff at higher temperatures. But there's a handful of compounds that actually became less soluble at higher temperatures. And one example of that is calcium hydroxide. Calcium hydroxide is an example of a solid that if you heat it up, more solid falls out, which is kind of weird. That's like counterintuitive. It's kind of, yeah, weird. And so it's weird, so I kind of waved my entropy magic wand around and said, oh, it's because of entropy. So let me show you why. So I gave you all the thermodynamic data here. I gave you delta H, delta S, and delta G of this reaction. Notice that all of these are knots. So these are table values. Table values are measured at standard conditions, 298 Kelvin. So I want you to calculate what is KSP at two different temperatures. I want you to calculate what is the KSP for calcium hydroxide at 25 degrees Celsius, and I want you to tell me what it is at 100 degrees Celsius. So the first one at 25 degrees Celsius, this one is rather straightforward. 25 degrees Celsius, is that standard temperature? It is. So am I allowed to use a table value? You are. All right, so at 25 degrees Celsius, this is standard temperature. All right, standard temperature. So you are allowed to use delta G naught. We are simply going to just use this term right there, that value right there, right? So we're going to use delta G naught equals negative RT ln K. right? So at 25 degrees Celsius, so we're going to simply use 30.4 times 10 to the 3 equals negative 8.314. Temperature 298, ln K. So natural log of K, we are just solving for what K needs to be. All right, so solve for K, take e to the both sides. I'm just going to skip these steps. So you're going to divide both sides by these terms and then take e to the both sides. So you get KSP equals 4.8 times 10 to the negative 6, sure. All right. So this is at 25 degrees Celsius. This is at standard conditions. So you are allowed to use delta G naught from the table values. So now let's look at the follow-up question. Now I'm asking you, what is the KSP at 100 degrees Celsius? Is that at standard temperature? 100 degrees Celsius is not. Am I allowed to use this number? I am not. Delta G is a different number at 100 degrees Celsius. Well, how am I going to get delta G at 100 degrees Celsius? Read the rest of the sentence. It's calculate at 100 degrees Celsius, assuming delta H and delta S do not change with temperature. So delta G changes with temperature, changes, I guess, away from 25 degrees Celsius, but we're going to assume that delta H and delta S do not change with temperature. Change with temperature. So this is where we're going to use this equation again, all right? I don't know what delta G is at 100 degrees Celsius, but I'm going to assume delta H and delta S don't change, and I'm going to put T is 373 Kelvin in for that that third equation there to get the new delta G at these conditions, and then plug that into my K expression that I need, right? So yeah, we basically need a new delta G at 100 degrees Celsius, all right? And we're gonna do that using the equation delta H minus T delta S, right? So that new equation, or that new delta G value, will be equal to, okay, so delta G at 100 degrees Celsius is equal to the enthalpy value, so negative 16.7 times 10 to the 3 joule per mole, minus temperature, so 373 Kelvin, so this is at 100 degrees Celsius, times the entropy term, so times negative 157.89 joule Kelvin, all right? And so we get that, we have a new delta G value at 100 degrees Celsius. It is, I wrote it right there, positive 42.2 times 10 to the 3 joules. So we see that delta G actually becomes a little bit more positive at 100 degrees Celsius, and it's because entropy change is a negative value. That's actually why, right? So this is the number. This is the delta G value, okay, that we want to plug in to the equals negative RT ln K, all right? And so in this case, when we plug in temperature here, this number is going to be 373 Kelvin. R is still the same. We're going to calculate a new value of K in this case. What a lot of students will do in answering this question is they recognize, oh, 100 degrees Celsius, but they'll just reuse this delta G naught. That delta G naught is only good at 273 Kelvin. So we have to figure out what is the new delta G naught at non-standard temperatures, and to do that we use entropy and enthalpy. That's if you're at non-standard temperature conditions, that you have to get that new delta G value using delta H and delta S before you plug it into the negative RT ln K. And so when you do this, this new different delta G value equals negative RT ln K, and you solve for K, you get the KSP is a slightly smaller number. It's 1 times 10 to the negative 6. So we do see, in fact, that calcium hydroxide becomes less soluble at higher temperatures. And the reason is because delta G becomes a more positive number. We see that here, all right? That delta G at room temperature is 30 kilojoules, but at 100 degrees Celsius, it's 40 kilojoules. So it becomes less this reaction becomes less spontaneous at higher temperatures, and it's because of the sign of entropy. Okay, so that's basically the hardest part of this chapter, is navigating delta G, delta H, and delta S, when to use table values, when not to, and the equations related there, and how Q conditions, non-equilibrium conditions, fit in there in predicting things like Le Chatelier's principle. All right, so let's just take a minute and finish off the last part of this chapter, and that's just reiterating the idea, we looked at spontaneous reactions. Spontaneous just means irreversible. It just means entropy change of the universe is positive. It means Gibbs free energy change for the reaction is negative. Spontaneous processes are irreversible. Spontaneous processes are not necessarily fast. Fast is kinetics. That's completely different. We know that this reaction, the hydrogen balloon reaction, is pretty fast. But on the flip side, like when I lit that candle, that reaction's rather slow, right? It's a lot slower. So what we see here is that thermodynamics and the second law has nothing to do with speed. That's actually kinetics and activation energy. So let's look at these two reactions, all right? Here is the combustion of diamond, all right? So take diamond, react it with oxygen, you get CO2, right? So I calculated delta G of this reaction for you. So based upon this value, is this reaction spontaneous? It is, yes. Burning a diamond, if I wanted to, is spontaneous. Once I get it lit, it'll burn on its own. Are combustion reactions fast? I mean, yeah, they're pretty fast. I mean, they happen within our lifetime. Right? They happen within our lifetime. If I, set fire some diamonds, it'll probably finish by the end of the day, depending on how much I have. Okay. So like all combustion reactions, they are usually spontaneous, usually fairly fast. Now let's look at this reaction. All right. So taking the table values. All right. So I have a bunch of table values, O2, CO2, diamond, graphite. If you do products minus reactants for this reaction, turning a diamond into graphite. So if you look at the table, you grab the delta G's for the products minus reactants. This is the overall Gibbs free energy change for this reaction. Is this reaction spontaneous just based upon the numbers? It is, because delta G is negative. What am I describing? I'm describing the conversion between a diamond, beautiful sparkly diamond, into pencil lead, graphite. We just proved, just from table values, products minus reactants, that this is a spontaneous process. But think about it. Is this process fast? I don't think so, right? I don't think so. Like, do you know anyone who received a diamond jewelry and it converted to graphite in their lifetime? No. What's the saying about diamond? Diamonds are forever. What did we just prove? Are diamonds forever? They are not forever. We just proved that the conversion from diamond to graphite is spontaneous. It will happen on its own eventually. It doesn't happen fast, but it'll happen eventually. So diamonds are in fact not forever. They will all spontaneously convert into graphite someday. I don't know when, probably not in our lifetime, but they are not forever. All right. That graphite is actually much more stable. All right. So yeah. Again, spontaneous just means that delta G is negative. So here's an example, diamond to graphite. This process is overall spontaneous because we have this lower, we're going to a more stable energy state. Delta G is negative, but because of the activation energy it requires to go from this process, diamond to graphite, this process is actually very, very, very slow. I looked it up. We were all interested in it. We looked up what is the activation energy for diamond to graphite, and it's a crazy high activation energy. So it's a very, very small, slow rate constant that we see, all right? So yeah, it's probably not gonna happen in our lifetimes. So just, I wanted to reiterate that spontaneity does not necessarily mean fast. It just means it'll eventually happen. And diamonds aren't forever. Okay, so we got 20 minutes left, so I'm going to go back to chapter 20. So this is the end of chapter 19, so we're done with 19. So what does that mean? Homework for 19 is due on Monday, yes. And so we will jump back into chapter 20 now. Hold on, chapter 20. Boop, boop. Okay, chapter 20, where we are talking about voltaic cells. So let's just go back to our voltaic cell stuff, okay, where we are looking at electrochemical cells. We are still actually talking about spontaneous reactions, all right? We're talking about spontaneous reactions, but we are relating them not to like, really fast combustion reactions, but we're actually looking at more mild electrochemical cells. So what we see here is once I set up this voltaic cell, this reaction is only spontaneous. Now I can use that term, spontaneous, to my heart's desire now. This reaction is only spontaneous in one direction, going from anode to cathode. The electrons will only go from anode to cathode. It will not go in the other direction. And why? It's because delta G is only negative in one direction and not the other direction. So that's why, some things are solely the anode, some things are solely the cathode. So what we see here, zinc is our anode. It's losing electrons, the zinc strip, and then those 2 electrons are going in to reduce copper 2+. At the cathode. So reduction is gaining of those electrons. So we see that, although we can't see it, electrons are going from this kind of silvery strip going through the motor here, and then the electrons are traveling to this copper strip. And so right now we're just harnessing those movement of electrons, but we can also calculate the cell potential that's produced, the voltage. So just a comparison, I think if we calculated the standard cell potential for this cell, we have copper and zinc, we would get, I think, a value of 1.1 volts, with zinc being the anode and copper being the cathode. To put that into perspective, so this is producing 1.1 volts. A standard like AA battery is about 1.5 volts. Your socket, like your outlets, are 120 volts, just to kind of put it into perspective. So here I'm going to show the voltage, all right, just to show you that we are producing a potential. All right, and so if you read this, it says 1.08 volts. So very, very close to 1.1. We've been running this demo all week, so we see that the concentrations are a little bit different than what they probably started with earlier this week, so the voltage has changed a little bit. So let's just keep you going. Keep going. All right. All right, so let's continue working with identifying our cathode and anode using this table to calculate our overall cell potentials. But remember, what's the caveat with table values? They have to be at standard conditions. So these concentrations are 1 molarity copper 2+, 1 molarity zinc 2+. That's at standard conditions. That's why we can say 1.1 volts. But what we'll learn here is, well, what if we make a cell, an electrochemical cell, that's not at standard conditions? What if they're not 1 molarity everything? That's where we kind of use another equation with Q conditions to calculate those voltages. All right, so let's continue using cell potentials. So let's look at these two, I guess, 3 half reactions and determine what combination gives us the largest cell potential. So EMF just means E cell. Okay, which combination gives us the largest bang for our buck here? And so the equation we want to use is that the overall cell potential is cathode minus anode. So in order to get the most positive cell potential, don't you want a very positive cathode and a very negative anode? That's the idea here. So if you look at our 3 options, we probably want this IO minus thing to be our cathode because it's the only one that's positive. But then the first reaction with the gold bromide thing, this is going to be our anode because it's the most negative, has the most negative cell potential. And so we'll just ignore that middle one. Okay, let's ignore the middle one. All right, because what we see is that this combination, a positive number minus a very negative number, gives us a very positive number come out. So E cell will be equal to positive 0.49 minus negative 0.86 volts. And so we see that this combination gives us a nice voltage, positive 1.35 volts, right? So we want this IO minus thing to be our cathode and then the gold bromide to be our anode. So we've identified the cathode and the anode, but notice that both of these reactions are written as reduction half reactions. So to write the overall balanced equation, which includes a reduction and an oxidation, we have to flip one of the reactions, all right? So cathode, our cathode is where reduction happens, but our anode is where oxidation happens. This reaction written right here, this is not oxidation, this is reduction. So we have to actually flip this reaction before we add them up to give the overall balanced equation. So the cathode reaction, we can just write that one as is. It didn't change because it's already in the reduction form. So cat reduction, I'm just going to rewrite it. IO minus plus water plus 2 electrons gives us I minus and 2 hydroxides. But I need to flip my anode reaction because at my anode, that is where that is where oxidation occurs. So I need to flip it. So the reaction that's actually happening is gold plus 4 bromides give us that gold bromide compound and then 3 electrons. So now I have a proper, electrons being produced at my anode and consumed at my cathode. All right, those are my 2 half reactions. But can I just add these up as is? I can't because the electrons do not match. So I need to make sure that the number of electrons match. So I need to multiply my cathode reaction by 2 and my anode reaction by, no, I messed up. That one by 3, this one by 2. So then 6 electrons cancel on both sides. So you just have to be careful with your coefficients. So the coefficients on my anode are 2, 8, 2, and 6. And then on my cathode, it's 3, 3, 6, 3, and 6. So now when I add up these 2 reactions, the electrons cancel. And so we get 2 golds plus 8 bromides plus 3 IO minuses plus 3 waters give us 2 gold bromide compounds, 3 I minuses, and 6 hydroxides. And so that would be our balanced equation. So here I gave you the half reactions, but you still had to identify your anode was oxidation, flipping it, and then go through the same process of canceling those electrons. All right, in this process, N would equal 6 for fun, because 6 electrons cancel in the background. All right, so yeah, we can do this. All right, so let's do some other inspection of the cathode minus anode equation. All right, your E cell is cathode minus anode. Both of them are in the reduction form. So in this case, I'm telling you that the copper's reduction potential is positive 0.34. And then I'm setting up 2 different experiments, 2 different cells. And in these 2 different cells, I'm giving you the overall potential. And so in the end, I want you to tell me, given these 2 observations, what is the cell potential of this X, this mystery substance? So we're going to use this equation. The overall observed cell potential is cathode minus anode for all of these, but we need to make sure that we identify the correct thing. What is your cathode? What is your anode? So let's look at this first cell. Copper is being what? Reduced. Yeah, it's going from +2 to 0, so it's being reduced. It is your cathode. Nickel, therefore, is being oxidized. It is your anode. So that means this cell potential that is measured, it's 0.62, is equal to the cathode cell potential minus the anode cell potential, or sorry, reduction potential. So which one of these do we know already? Do we know the cathode's reduction potential or the anode? The cathode. Look, copper is being reduced. It is the cathode. I gave you the reduction potential for the cathode. So I'm going to put this number in the cathode spot. But if the reaction was different and copper was being oxidized, then we would put that number in the anode spot instead. So we have to deduce that copper is in fact being reduced in this example. So we're going to set up an equation where, okay, the measured 0.62 volts equals the cathode's reduction potential, so 3,4, minus whatever the anode reduction potential is. And so I think if you solve for that, we get that the anode, the reduction potential for our anode, in this case it's nickel, equals something. I think it's negative 0.28. That sounds right? Maybe, yeah, volts, yes. So that is nickel's reduction potential, right? And it is the anode. So we're going to use that piece of information for cell 2, because look, nickel is being what in this reaction? It is also being oxidized. It is the anode again. But this time X, and this is what we want to figure out, is being reduced. It is our cathode. So we're going to do the same exact thing, that the measured cell potential, 0.52, is the cathode minus the anode. But this time we know the reduction potential for which one? The anode, yeah, because we just figured out what zinc's was. So here I don't know what the, I don't know what the cathode's reduction potential is. That is X, the X mystery substance, but I do know the anode, which is nickel. So in this case, putting it all together, I think it's positive 0.52 volts equals the cathode's reduction potential, which I'm trying to figure out, minus the anode. We got that before. It's negative 0.28 volts. And so we get that the reduction potential for our cathode, which is X, is equal to positive 0.24 volts. All right, so in this example, it's tricky because, you know, our cathode and anode, I didn't explicitly tell you what is the cathode and anode. You had to figure it out and see how we could place those known values into the equation in the appropriate spot. All right, so that is the X reduction potential. It is your cathode. All right, so we got a couple more minutes. So how else can we use reduction potential tables? It's by inspecting the values and interpreting strength of oxidizing or reducing power. So we have to be careful with language here, because these tables are always written in the reduction form. So always in the forward direction where electrons are being gained. But I can also ask you questions on what is easiest to be oxidized. But these are reduction values. Oxidation is the opposite direction, right? So we got to be careful about that. So let's go through this table. So remember, this table is a reduction half reaction table. So if we look and see, okay, these answers are pretty straightforward. Which species is the strongest strongest oxidizing agent? So think about it this way: an oxidizing agent is a thing that is reduced. So really, I am asking you, if I ask you what is the strongest oxidizing agent, I'm asking you what is the thing that is easiest to reduce. All right? Easiest to reduce. That's what an oxidizing agent is. So you are looking for the largest reduction potential, right? These are reduction half reactions. So if you look at all of these, which thing is easiest to reduce? It's the one with the largest reduction potential. It is going to be silver plus. Silver plus is the best oxidizing agent because it's the easiest to reduce. It has the most positive reduction potential. If you put a positive number right here in cathode, much more likely you're going to get a positive cell potential out, all right? Versus which species is the weakest oxidizing agent, what kind of number do you not want to put in this spot? You don't want to put a negative number in the cathode spot because then you're more likely to get a non-spontaneous cell out. So what we see here is that the most negative value, zinc 2+, is the crappiest oxidizing agent because it is the hardest to reduce. It's the hardest to reduce. We're looking for the most negative reduction potential here, right? Okay, so those are the reduction potentials. We just looked at the reduction potential straight up because I was asking for oxidizing agents. Oxidizing agents are things that are reduced. So now let's think about it the other way. I can ask you, what is the best reducing agent? What is the best or what is the worst reducing agent? But we got to be careful here, okay? Because this reaction is a reducing, like a reduction reaction, whereas zinc 2+ is an oxidizing agent. But if you reverse the reaction, zinc is now being oxidized. Now zinc solid is a reducing agent. If I flip this reaction, don't I flip the sign of this half reaction? So what we see is zinc 2+ is a really, really crappy oxidizing agent, but zinc is a great, great reducing agent. Does that sound familiar? Yes, it does. And it's because the sign flips here. So what we see is that the reverse of a reduction half reaction is an oxidizing reaction, all right? Things that are oxidized, these are your reducing agents. So what we want to see here is that the strongest reducing agent, it's the thing that is oxidized. So you are looking for the largest oxidizing half reaction value. But the thing is that this table doesn't give us oxidation reactions. So you're really looking for the most negative reduction value. So in this case, zinc is our strongest reducing agent. But you want to make sure that you point to the product, all right? And so same idea here. The weakest reducing agent is going to be silver solid, because it has the smallest oxidation potential, or it has the largest reduction potential. But of course, we are pointing to the product. So I want to contrast this to, acid-base chemistry as well. We said that the stronger the weak acid, the crappier its conjugate base. Same idea here. The stronger your oxidizing agent, the thing that is created is going to be a really crappy reducing agent. Or here, zinc 2+, really crappy oxidizing agent, but the product there, zinc solid, is a great reducing agent. All right, so we'll stop right there. Sorry, I went over. So chapter 19 homework is due. We'll finish the last part of this chapter in preparations for midterm 4 on Monday.